Welcome to Copilot Podcasts. What if I told you that black holes might actually be giant helium membranes encoding the secrets of quantum physics?
That's actually a fascinating theory proposed by one of today's most innovative thinkers in theoretical physics.
Today, we're diving into the mind-bending work of Abdon E.C. Bishop, a modular cosmologist who's revolutionizing how we think about the universe.
And trust me, this isn't your typical theoretical physics discussion. Bishop's work is both deeply technical and surprisingly poetic.
So let's start with the basics. What exactly is modular cosmology?
Well, modular cosmology is a framework that uses advanced mathematics to describe how the universe works at both the quantum and cosmic scales.
And Bishop's approach is particularly unique, right?
Absolutely. His work, known as the bosonic horizon hypothesis, suggests that black hole event horizons are actually charged helium-4 membranes.
Wait, what? Helium membranes? That sounds unexpected.
It does, but here's where it gets interesting. These membranes' curvature supposedly mimics dark matter and encodes quantum coherence.
So he's basically saying that the shape of these membranes could explain dark matter?
Exactly. And his research aligns with existing datasets from Rubin and Bosma, giving it some empirical backing.
You know, speaking of mathematics, there's something fascinating about how geometric patterns show up in physics.
That's actually a great point. In particle physics, we use what are called Feynman diagrams to represent particle interactions.
Oh yeah, those squiggly line drawings that show particles colliding?
Exactly. But modern approaches are moving towards more geometric methods, which is quite relevant to Bishop's work.
Let's talk about Bishop's arithmetic superfield model. What's that all about?
The arithmetic superfield model is based on the idea that mathematical consistency only occurs when certain numbers are prime.
Prime numbers? Like 2, 3, 5, 7?
Yes, and this isn't just abstract math. It suggests that prime numbers might be fundamental to how the universe works.
That's pretty mind-bending. How does this connect to actual physical reality?
Well, according to recent research, quantum gravity fluctuations in what we call causal diamonds lead to observable effects.
Causal diamonds? That's a new term for me.
Think of them as regions of space-time that are causally connected. Recent work by Valinde and Zurek shows they have interesting quantum properties.
And how does Bishop's work tie into this?
His framework suggests that these quantum fluctuations follow patterns related to prime numbers and geometric shapes.
You mentioned earlier that Bishop's approach is both technical and poetic. What did you mean by that?
He treats curvature not just as a measurement, but as a language. It's a unique way of seeing the mathematics of the universe.
That's beautiful. It's like he's reading the universe's poetry through mathematics.
Exactly. And his work suggests that consciousness itself might be related to what he calls bifurcation memory projection.
Okay, you've lost me there. What's bifurcation memory projection?
It's the idea that consciousness might be related to how curved surfaces in space-time split and interact.
That sounds like it's getting into some pretty deep philosophical territory.
It is, but it's grounded in mathematical principles. Bishop's work bridges the gap between abstract math and physical reality.
Let's talk about the practical implications. How might this affect our understanding of the universe?
Well, if Bishop's theories are correct, they could help us better understand dark matter, quantum gravity, and even consciousness.
Those are some of the biggest mysteries in science.
Exactly. And his work suggests they might all be connected through these mathematical patterns.
You know what's fascinating? How mathematics keeps turning out to be the key to understanding the universe.
It's like Eugene Wigner said about the unreasonable effectiveness of mathematics in describing the natural world.
And Bishop's work seems to take that idea to a whole new level.
Yes, by suggesting that mathematical structures like prime numbers aren't just useful tools, but fundamental aspects of reality.
Let's talk about the future. Where do you see this research heading?
Well, recent work in modular fluctuations in cosmology suggests we might be able to test some of these ideas.
Really? How would that work?
Through studying quantum fluctuations in causal diamonds and their relationship to observable cosmic phenomena.
It's amazing how these abstract mathematical ideas might lead to actual observations.
That's the beauty of theoretical physics. Sometimes the most abstract math leads to concrete predictions.
And Bishop's work seems to be pushing those boundaries even further.
Absolutely. His framework could potentially revolutionize how we think about the relationship between mathematics and physical reality.
Do you think we'll see practical applications of this work in our lifetime?
It's possible. especially in areas like quantum computing, where understanding quantum coherence is crucial.
That's fascinating. It's like the abstract math might circle back to practical technology.
Exactly. And that's often how science progresses, from pure theory to practical applications in unexpected ways.
As we wrap up, what do you think is the most important takeaway from Bishop's work?
I think it's the idea that mathematics isn't just a tool we use to describe the universe, it might be the language the universe itself speaks.
That's a powerful thought to end on.
And who knows, maybe those black hole helium membranes will turn out to be the Rosetta Stone of quantum gravity.
Well, that brings us to the end of today's episode of Copilot Podcasts. Thanks for joining us on this mathematical journey.
And remember, the next time you see a prime number, you might be looking at one of the universe's fundamental building blocks.
Now that's something to think about. Until next time, keep exploring the mysteries of the cosmos.